Hi everyone, welcome back to the Altium On Track Whiteboard series, now part of Altium Academy. I'm Ben Jordan, and today we're going to talk again about RF and microwave PCB design. And as promised, after the last episode, which was kind of long, full of information about couplers and how those work, we're going to take that one step further now and talk today about filters. But we're not going to make it huge. Long episode like last time, so stick with me and we'll talk about how filters are usually realized in printed circuit board design. So I want to refer really quickly back to episode 3 where we talked about stubs, and we talked about short circuit stubs and open circuit stubs. And if you recall from watching that episode, a transmission line segment that's shorted to ground off of another transmission line on a printed circuit board. Okay, so let's draw that. Let's say we have some kind of source. Let's go black there, actually. Have a source coming in. We have our system impedance, Z0, and some transmission line segment. And if we have another segment going to ground like this, down the line, okay, and this is all Z0, then if this segment here is a quarter wavelength, then at the resonant frequency of our system, the center frequency where that is 1/4 wavelength, this short circuit actually appears like an open, as you recall. And similarly, an open circuit stub will appear as a dead short at a quarter wavelength. So there's a sort of duality here between transmission line segments on the PCB and other elements, namely inductance and capacitance. So how can we use that to make filters? Well, the basic approach is we can say that a transmission line segment shorted to ground, right? When the electrical length of that, let's call it theta, is less than a quarter wavelength, which is 90 degrees, then this appears to be a shunt inductance, okay? And there's a transform where inductance has this inductive reactance, XL, which is essentially the impedance of a perfect inductor. So the equivalent inductive reactance is omega, which is 2 pi times the frequency. It's in radians, omega L, right? The equivalent is when this is behaving like an inductor, when it's less than a quarter wavelength long. This is a simple transform. The impedance of the transmission line, Z0, that's this segment, Z0, times the tangent of the electrical length. So I'm going to create a new page here. Just go over. So we can do the same thing similarly if we have a transmission line and we stick an open circuit segment let's say that's a quarter wavelength long. Well, let's say that the length of this is less than a quarter wavelength, okay, or 90 degrees. Well, that is capacitive in that case, which we recall from our earlier episode on stubs and transmission line segments. So if you have a capacitor, a shunt capacitor, and why is this shunting? Well, because remember, this is a transmission line segment on a PCB. There's always ground plane underneath it. If you break up your ground plane, or if you put this on the board and have a void underneath where it's just dielectric but no ground plane, then it won't behave this way at all. It'll have a different impedance and it'll have capacitance out to other objects. It won't be a proper formal transmission line segment. But because there's ground plane under it, that is capacitive, right? So this appears like a shunt capacitance. And capacitance, of course, also has reactance. Capacitive reactance is 1 over omega C, right? And that's equivalent to this transmission line segment. And to get the capacitive reactance of a transmission line segment open circuited, less than a quarter wavelength long, the transform is the impedance of the transmission line segment, Z0, cotangent theta. And this, it's important to remember, this only works when these are at or less than a quarter wavelength long. And similarly, if we have a series element in a transmission line of impedance Z0, then if theta is less than an eighth wavelength long, or 45 degrees, in that case, this is like equivalent to series inductance in your transmission line. And so you can see you can easily build up the elements at microwave frequencies of L's and C's needed to build up filters, passive filters. And that's 99% of the time how it's going to be done. Okay? Similarly, if we have a series transmission line segment, it also has capacitance to the ground plane. So if you want to work out what's the inductance, you can use this one, right? Again, XL equals omega L. And the transform here, the inductance of a series transmission line segment is given by omega, XL is Z0 sine theta, only when theta is less than 45 degrees. And then we have, how do you find the capacitance of that segment, the capacitive reactance of that segment? When that's less than eighth wavelength, or 45 degrees, again, you can work out the series, it's series L or shunt capacitance. Okay, because every transmission line, every trace on the circuit board, you could break it down into piece by piece, has capacitance to the ground plane. So it's always there. So if you want to say, well, for this little portion of trace on my PCB, what's the equivalent capacitive reactance of that section? And you can work that out using this transform as well. We have capacitive reactance is 1 over omega C. And of course, XC here is going to be the inverse, like it is capacitance and inductance. They're always inverse of each other. Okay, so that's Z0 over sine of theta. Again, only when theta is less than 45 degrees. So if you have a longer trace, you could work out equivalent piecemeal by dividing it up into eighth wavelength sections and using the transform, and then putting all those capacitors in parallel and inductances. And of course, that's what you get with a transmission line. If you look at any normal lumped element sort of view of transmission lines in any electrical technology textbook, you'll see a transmission line is usually first presented like a bunch of discrete L's. And this again goes back to our first episode where we talked about the introductory transmission line theory, series L's and parallel C's. Well, of course, series L's, shunt C's. So, of course, we have series transmission line segments, we have shorted parallel transmission or shorted shunt segments, we have open shunt segments, and all of these can be used to build up basic filters, like the one I have right here. This one is just showing you that on the front camera there. You can see this one has just series transmission line and quarter wavelength segments separating those with some shunt inductances, but of course they're a quarter wavelength long. So what does a short circuit appear like as? What does it appear as? It appears as an open at the resonant frequency or the center frequency of this, but this is a band pass filter. Obviously at DC or low frequencies it's a dead short to ground. At high frequencies, where these are a quarter wavelength long, these are open and passing, and at higher frequencies these become more inductive again and cause a roll-off in the high frequency response. And of course, I can just put up a screenshot here. This is the actual measured frequency response from the VNA of this particular filter. And so filters can be built up of those kinds of elements. And you also recall from the stubs episode where we talked about just a single stub like this one. This is a quarter wavelength stub. I'll get that in focus there. That quarter wavelength stub forms a very narrow notch filter at the resonant frequency because that open circuit stub appears to be a dead short when that's a quarter wavelength long. And here's the frequency response from the VNA of this one, which I captured earlier. And of course we can broaden the notch and make it a broader frequency response by adding capacitance, and one way to do that is to use a radial stub. And you'll see these in a lot of really commonly used in RF and microwave boards for matching networks and filtering networks to have these as bow ties. Maybe to shrink the size of this, you put, instead of one big one on one side of the transmission line, you might put two smaller ones on each side. But this is like a huge capacitor. I'll just throw up a screenshot here of another one. I don't have the board with me right now, of a low pass filter that uses a series of those radial stubs of thin trace segments. So those thin trace segments are very inductive and appear as series inductances. So this would be something like this. So if we have our input, we want series inductance, we're going to have big capacitance to ground, and we're going to have more than one of those because we put, just reduce the space required, we put a couple of radial stubs and then a couple more separated by more inductance. Right? And then of course we have some transmission line segments on either side of that, on the input and the output of the filter. And so this is a pretty good low pass filter. You can see at DC everything's going to get through. At higher and higher frequencies we have more of that shunt capacitance shorting out the signal, and the higher and higher frequencies also pass less easily through the inductors in series. So series inductance, parallel capacitance gives us a low pass response. And here's the frequency response from the VNA of that particular one. So how that looks on a printed circuit board, you've already seen from the screenshot. I've just put that screenshot up there. And how do you calculate these? Well, you can use some of those transforms I showed earlier. And here's a few more that you can use, because there's always some inductance, just like we looked at with this this transmission line segment, it's an open circuit, so it appears like a short at the center frequency, where that's a quarter wavelength long, but then it becomes an open again at higher frequencies, and then at a multiple of a quarter wavelength, it becomes a short again, and so on. And so you can see there's this repetitive nature to the frequency response. So this has capacitance to the ground plane, but it also has inductance in its length. And so what does that mean? It means if you have a transmission line segment going to ground, say, and that's the electrical length of that is a quarter wavelength, then this is a resonance circuit. And similarly, if like these here where they resonate, there's a notch frequency response we saw earlier. Those transmission line segments, so this goes nowhere, that's an open segment, okay? These are Z0, and that's a quarter wavelength long. Okay, so this one exhibits this kind of frequency response. This one is the opposite. So on one side it's inductive, and on the other it's capacitive. And likewise here, on one side it's capacitive, on the other it's inductive. And they're the opposite, the inverse of each other. The shorted segment versus the open segment. And so a shorted segment has this transform where Z0 is pi on 4 omega inductance, and that's for a parallel resonant tank circuit. And then we have this transform, which you can use for filter design, pi on 4 omega L. So it's the same when this is a transmission line segment that's 90 degrees or quarter wavelength long. Similarly, for an open circuit transmission line segment, we have that's got series inductance, so it looks like this, and it has capacitance as well to ground, to the plane underneath the transmission line segment. So it's equivalent is when Z0 is 4 on pi, so that's inverted, omega L. Then of course you have transmission line segments that exhibit some series resonance as well, and that happens when you're half a wavelength long. So that would be if you have a segment that's lambda on 2, then it appears like a series LC resonance circuit where the reactance is omega L, and we have the reactance of pi on 2 because it's half a wavelength long, Z0. And these are just handy transforms. I didn't come up with these, of course. They're well known in the industry. They're in a lot of textbooks for RF and microwave design. But a really cool site that you might like to use as a resource for this is, which one is it? It's RF Cafe. So there's a really cool chart that has all of these in it on RF Cafe. So RF Cafe, thank you for your contribution to our education in this regard. Let's go to a new page. Now, of course, you can also introduce more capacitance in series if you want a high-pass filter. And so how would you do that? Think of a capacitor as being two plates again. You have two conductors near each other, with a lot of E-field coupling between them. That's a natural high-pass element. And of course, if you have some parallel inductance or shunt inductance to ground, that's your typical high-pass filter. And of course, we have series inductance, like a normal transmission line trace with shunt capacitance. So we know we can add capacitance by putting stubs. We can add inductance by adding thinner trace segments or trace segments that have a greater separation from the plane. Of course, we want to match impedance through the whole thing. So that's a low-pass filter. And to make a band-pass filter, you combine these elements together. So you would have series and parallel capacitance and series and parallel inductance. And of course, you choose the reactances of these elements at the corner frequencies you need to get the response you want. And the bandpass, so you'd have F1, F2, and you would also choose those, not just to maintain system impedance and get the response you want, but to damp the filter according to the amount of passband ripple you want, because you know there might be something like this going on. Passband ripple. And there are many different types of filters that have different numerical techniques for deciding the component values and calculating the component values, like Chebyshev, Bessel, Butterworth, elliptical, and so on, to get the kind of pass band or low pass or high pass response and slope that you need. And I'm not going to do that here. This is not an electronics engineering class on filter design, but I will point out there are a number of really good calculators out there. Many of them are free. You can download numerous ones from semiconductor manufacturer websites, and there's a lot of open source ones too. I happen to use one in a program called Kooks that has a filter synthesis tool that's really, it has a few things. It's missing some things I'd like, but it's open source, so it doesn't cost me anything, and you can try it too. And it gives you the transmission line segment lengths that you need to calculate things like this filter here. This was done actually using that tool, and it's free. And of course, you jump into Altium Designer and build your filter components and lay it all out on a board and make it up, and it works brilliantly. So there's one more thing just to introduce here, because I've talked about series capacitance, and you get that in transmission lines on a PCB by either introducing gaps, and so there are filters you can build where your transmission line segments may have gaps, and this is effectively like a series capacitance in your line. It will be a little bit lossy, but when you need to filter something, you need to filter something, and this is just one method of doing it. You can introduce capacitance. You could also introduce series capacitance by doing something like an interdigitated. This is a very simple transmission line segment way of doing it, where there's additional coupling here, so you reduce the amount of losses in this, and you can actually build an interdigitated capacitor by having many fingers of conductor off your two transmission lines going like this. And you'll see this a lot in RF designs. And again, I use Waddell's transmission line design handbook. Has all the formulas for calculating these things in it. Great resource. Hard to get. If you can get it, do your best to get it. Okay, so there's a number of ways of introducing capacitance. Now remember, in the last episode, we were talking about couplers, and we looked at our 90-degree hybrids to start with, but we ended up looking at directional couplers which use electromagnetic coupling. And that's, again, where you have transmission line segments that come close to each other for a quarter wavelength or more. They're pretty broadband devices, actually. So you can have this kind of thing. All right. And we're coupling signals here. We have capacitive coupling and magnetic coupling here. So we can actually make use of this. This has a certain bandpass frequency response, and it's a very useful way of also constructing filters. So we could actually have a transmission line coming in, and instead of having the directional coupler look like this, we can place with a quarter wavelength overlap, or some multiple thereof that suits our needs. We can have multiple segments overlapped, and they are couplers in between the segments, and each of these sections, typically a half wavelength long, forms a resonator, and it resonates at the center frequency that we want for our bandpass filter. And these can be made to be reasonably broad, usefully broadband devices as well. So let's go to a new page and look at one of those. So I'll just switch over here to the design I did previously. And this is the idealized frequency response. So this filter is actually modeled as a series of directional couplers, or coupled line, or differential pair segments, you could call it. And although each resonator is a half wavelength long, really it's a quarter wavelength strip of differential pair or coupled line, like a directional coupler, connected immediately to another one, and then immediately to another one, and so on. And you can cascade these down. And so we get capacitive and inductive coupling between each of these segments. So that looks like, here we're coming in, we have our coupled line, we have an incoming transmission line, then we have a directional coupler, or a coupled line segment, and another coupled line segment, and another coupled line segment, each of those quarter wavelength long, and then our lead out. And this forms a really good bandpass filter. And how that looks on an actual PCB, I just wanted to give a shout out to Sierra Circuits, my friend there, Amit. Hi Amit, hope you're watching this. He had these boards made up for me for an RF design class I was doing last year. And they did turn these around in 8 hours. I was blown away because I just said, hey, I'm doing a class. And he's like, what's it on? Oh, RF. And he's like, do you want some boards made? Oh, sure, yeah. So I designed this really, really rushed and quickly, but they pushed it through so I could have these in time for my class, which is awesome. But looking at that up close, you see that top item there is a series of coupled line segments forming that bandpass filter. And that's done in a long line. So these can be shaped, curved. They don't have to be in a straight line. You can see I've done these at a slight angle because I wanted to make them go in a straight-ish line from connector to connector. So here's the thing. Here's the frequency response of that board. I'll just throw that up there, captured from the VNA. And here's the same design in the simulation program, or the synthesis program I mentioned earlier. And if you want, you can actually fold those things over. So you can have a coupled line segment that looks like this. Let's go black. Here's our coupled line segment coming in. All right. And this is our input. And we may move this, along, and that's really just for impedance matching our filter at the input. And we have this coupled line segment, right? We can do it this way. And then this would fold over. That's a quarter wave. We carry it on. So we've got a little bit more transmission line, enough to separate it so it doesn't couple on itself. And that may come to another segment that's coupled. And then that may go around to further segments. And you've all seen these before and probably wondered what kind of magic, black magic this is. It's just this kind of structure folded over to use less long. Instead of being really long, we've concertinaed the whole thing up to make it shorter and more convenient. And over here I did a coupled line segment at the beginning, but actually usually this, let's just delete some of that. Usually the way this works is our incoming transmission line segment goes straight to that first what we call a hairpin. So this is commonly referred to as a hairpin filter. And we do more segments if we want steeper side lobe or steeper walls on our filter. If we want a steeper frequency response, like more of a brick wall, you add more segments. Like any passive filter, you add more inductance. If you want a steeper walled low pass filter, you add more series inductance, more parallel capacitance at the corner frequency that you want. And then at some point you've got enough, and this carries on as the output to the filter. Coupled line filter. And this is a hairpin. And there's many other variations of these. But if you start to look at RF boards, and you'll start to see some structures like the things we've been looking at, by now you're getting a pretty good feel for what they all are and what they do, and what their circuit function is. And then the dimensions are a matter of where the frequencies are and what the responses are and how much loss is going to be in the circuit. I was going to say there's no easy closed form formulae for designing these things. You can do it piecemeal by breaking down every segment into its equivalent L's and C's. But when it comes to the coupled line filters, of course, there's those coupling factors involved as well. And so you could take a very tedious numerical approach to designing them, and you'll get pretty good results. But almost invariably, you'll want to use some software. And again, you can turn to plenty of good open source tools, or even some commercial tools. I've even seen little programs for sale on an individual ham radio operator's website that he wrote his own program for doing all the tedious numerical computation for you, and sells a program for $200 or something like that. Of course, it would be a really great project for anyone who's ambitious at scripting to do an Altium Designer script to do this, and maybe I'll do that someday in the future, but we'll see if I ever get time, hopefully. In the meantime, there's plenty of calculators out there, and it's not hard to build these things up and prototype them and play. If you really want to get optimized, you probably want to simulate these, and simulate them using a proper field solver. And so there are certain tools, of course, available for that. Many of them are super expensive, or you can use, again, open source software. But either way, there's plenty of tools available, and if you want to find a resource hub for those, check out microwaves101.com. Again, I mentioned that, and RF Cafe is another really good one that have a lot of links and resources to things that you can use. And again, I've designed this one using the filter synthesis in Kooks. Super easy to use, and built it up in Altium Designer using coupled line segments made into components, so it could easily be represented on the schematic side. And so again, here's the design, and here is the frequency response of this board here measured with the VNA. So it works pretty good. So that's all from me on RF filters on PCBs this time, and I hope you found that fascinating and useful. And I know it's just an introduction of the topic, but enough to give you a qualitative understanding of what's going on, so you can go forth and experiment on your own and do your own. And I look forward to showing more in the future and talking about things like antennas. So stay tuned. Please leave your comments and questions below, and check out the description below for links to different resources that I've mentioned in this video, and come back next time. I'm Ben Jordan, and thanks for watching. See you around.